Hi, everybody. This is Victor Lopez. I'm co-chair of the OPT working group within the Telecom Infra project, and I'm also a network architect in Telefónica. Today, I have the pleasure to be with you in this session called Towards Programmable Transport Networks, held in the Layer 1 to 3 World Congress 2020. The agenda that we have for this session is the following. We will start with an introduction about how transport networks are programmable, that it will be given by myself. Later, we will talk about Transport SDN reference architecture, and Vodafone will be the speaker for this part of the session. Thirdly, we will have a Telefónica colleague. He will speak about agile networking. And we will move towards use cases methodology that MTN will present. Finally, network intelligence will be covered by Telia in this session around towards programmable transport networks. Why are we claiming that transport networks are programmable? Let me go back a little bit and start with open networking. Disaggregation and openness is being part of our networks, and we have this disaggregation and openness from the home to the core network. If we start thinking about devices that we deploy at home, like set-top boxes or home gateways, they are becoming more and more open devices where we are internally from the operators, we are even doing the design of these pieces, and we are deploying it in the homes of the customers. If we move toward access, we have the initiatives around fixed open access and mobile open access, like Open RAN, for instance. And in the transport networks, we are seeing a trend around IP and optical disaggregation. How we can decouple the hardware and the software pieces, and instead of having just a single router from a given vendor, we can buy the solution to a hardware and a software manufacturer. Also, in the cloud environment, virtualization is a trend that is decoupling and changing the paradigm that we have in our infrastructure. In fact, this has forced the operators to move towards a cloud strategy, a telco cloud strategy, where we are creating our own data centers in our networks in order to change the operational model that we used to have with single devices for each of the network functions that we were deploying in our networks. Which are the drivers for operators to move toward openness? The first thing is efficiency. We believe that having an open network will help us to shape the solution that we want to deploy in our network, and will provide us a more efficient network, as we will use only the components or the systems that are shaped for the needs of the given solution. The second key point is the differentiation. There are some solutions that we are deploying in our networks which are not considering some of the factors specific for a given country, a given area, or a service that we are willing to provide. Having the capability to select the players, the features, and the software components will help us to differentiate the way that we are building our networks. And finally, we think that we need a stronger ecosystem, mainly with the challenges that we have in the future. In the following days or years, we are going to build our 5G infrastructure, and we need a sustainable deployment of this 5G. Having more players in our ecosystem will help us to have a better investment, in the sense that we will be more efficient solving the issues that we have nowadays with our networks. Which are the principles of this network transformation that we are facing to cope with more bandwidth and the 5G evolution? The first thing that we see in the network transformation is that we need open reference design and a framework that will be able to adapt to the needs of each of the operators. At the same time, we need an automation in the deployment of our solution. So zero-touch automation networks will help us to reduce the OPEX and the operational costs that we have in our daily activities, and this will facilitate the way that we scale our network. SDN programmable connectivity is mandatory for us in this in the future, because it will help us to work with the different vendor suppliers and solutions in order to create an homogeneous way to show the network to our OSS and to our upper layers. And SDN will help us to program and configure the network in a seamless manner. Cloud-based architectures, as I mentioned before, is one of the trends that is forcing us to change our IT infrastructure and even our network, because we have to move towards a cloudified scenario where we could deploy different network functions in different locations. And this is part of our journey in this network transformation. And finally, we need to a single simple converged network that will provide services for fixed and mobile customers. So this way we can have a more efficient and cheap network deployment infrastructure. I stated at the beginning of the session that I'm co-chairing the OPT working group. The OPT working group is the Open Optical Packet Transport Group within the Telecom Infra project, and we are working in the aggregation core and access segment, which is the area that we are covering in OPT. We start the design of devices and IP optical components from the cell-side router. So after the base stations, operators are deploying routers in order to provide layer 3 capabilities, and the cell-side router is the first device that we are designing in this scenario. In our case, as we are working towards open solutions, the first design that we have is the DCSG that is very close to the base station. After it, all the aggregation router, the optical transport, the optical transponders are also part of the scope of the OPT working group, and also the core routers that we are building in our backbone infrastructure. So why are here today all these operators talking about this network programmability? We think that the future networks will be disaggregated, and this is why we are working in this open network concept, and programmability is a must. It's going to be mandatory for us to deploy an SDN solution that will help us to provide a programmability of the network devices. Recently, in the week of the 6th of October, it was released an announcement within the Telecom Infra project, where 6 operators we were joining our forces in order to work around SDN capabilities. MUST is an initiative that the acronym means mandatory use case SDN transport requirements, and we are working together with the aim to show to present to the industry which are the requirements that we have as network operators. We have worked a lot in transport transformation. All of us, we have been leading different projects in order to improve our networks and prepare them for the future. And SDN come as part of this solution in this network transformation. However, this has happened as fast as we wanted for several reasons. And we believe that being together is going to be a way to show to all the industrial partners that are developing products to shape their solutions to the specific needs of the network operators. In this MUST initiative, we are co-signing a white paper that it will be published in the future. And these operators are Deutsche Telekom, Vodafone, MTN, Telia, Orange, and Telefonica. And all of us, we will co-sign this white paper, and this is why today we are explaining which are our view around network programmability. I'll start just presenting one one key piece of why SDN is mandatory for this open networking environment. When we decouple hardware and software in a given device, in this example, we are showing 3 different routers, the hardware and the software pieces becomes different for each of the vendors that we have on the network. If we mix and match solutions from different suppliers, it will be challenging for us to provide an end-to-end solution because we may end up configuring devices from different vendors in a very heterogeneous scenario. So having standard APIs, enabling this programmability is going to be key for us, as it will be presented in the following slides by the rest of my colleagues. And now I will pass the token to Jeff, who will explain about Transport SDN reference architecture. Please, Jeff, when you want.
Yeah, thank you, Victor. So I'm Jeff Bouquier. I'm from Vodafone, network architect at Group Network Architecture. So I will introduce you to the Transport SDN reference architecture that we are considering in this new must subgroup. So please, next slide. Okay, so the Open Transport SDN reference architecture is a hierarchical architecture. This is well aligned with the industry main architectures as ONF or IETF, ACTN, abstraction and control of traffic engineering networks architecture. And as you can see on this slide, the control separation between the technologies, IP MPLS or optical and microwave, is managed by dedicated SDN domain controllers. The SDN domain controller will control a set of network elements through a standard southbound interface that depend on the technology, of course, but not on the specific equipment vendor. Each SDN domain controller has also a standard northbound interface to communicate with the hierarchical controller. And the key role of the hierarchical controller is to aggregate demands from the operation support system, the OSS upper layer, which includes, for example, service orchestration, service and resource inventory, performance, etc., and exposes a standard northbound interface also for providing resource configuration abstraction and technology agnostic transport connectivity service definitions for consumption. The level of abstraction of the network resources exposed in northbound of the controllers will depend, of course, of the use case definition and the technology considered. Please note that the OSS layer is out of scope of a must subgroup. Must focus is on standard interfaces, detailed specification for each of the layers, as we will explain later. Leveraging, of course, on existing standards and young data models that are delivered by the main standard bodies. The practical implementation of the potential integration or replication of functional components, domain controllers or specific functions to deploy will be decided by each operator. So please go to next slide where we will introduce the main functional components. So the transport SDN reference architecture is definitely multi-vendor, and as a consequence, openness is a key assumption, meaning that each SDN controller shall be multi-vendor and manage multi-vendor underlying network elements. IP MPLS domain controller is mature today, in our opinion, and for this multi-vendor support, and because also IP routers interoperability at IP MPLS level is well proven. But this remains the target for the microwave and the optical domain controllers. The optical domain controller, what we see in the short medium term is to focus on the partial disaggregation scenarios with netconf and young open config data models to allow the optical SDN controller to manage third-party terminal devices, third-party transponders, to take advantage of the existing line system in place in the operators. The full disaggregation, of course, remains the long-term objective with the open management and control of several third-party vendor line systems. And for microwave, the proposed model is aligned with this multi-vendor SDN domain controller target as a vendor-agnostic configurator for the microwave network. And the transport connectivity service management is left to the hierarchical controller, which provides the management and control for this end-to-end transport connectivity services. So there is a set, as you can see on the slide, a set of main functionalities we all agreed on, and I will just focus on some key parts. So the real-time network database that you see in each controller, where finally you collect all the data from the network elements underneath, physical and logical information, and this information can be made available and can be queried through a northbound interface for inventory purpose, for example. The set of transport services and the traffic engineering information in each domain is also maintained and available through query through the standard northbound interface. The real-time topology view, which is a very important part of the SDN approach. So the controller, using standard network protocols such as BGPLS, for example, in the case of IP MPLS controllers, maintains a multi-vendor topology view of its domain, which can be exposed then to the hierarchical controller. But also, it could be used by external applications like network planning or whatever. The transport connectivity service implementation configuration enables the configuration, the modification, and the deletion of transport connectivity services. So between endpoints and the transport connectivity service parameters based on requests through the northbound interface. And the level of abstraction provided by the northbound will depend on the technologies and the use cases in scope. The path computation element. So this is a key part also of the architecture. It's a stateful PCE as defined in the IETF, and that is able to manage all the intra-domain transport connectivity, for example, the MPLS LSPs in the IP domain, and to calculate also new LSPs at service creation if required, or to optimize LSPs, also to optimize LSPs. The controller monitors also all the LSP status in the network, and one important point is to highlight that the protection switching, for example, is still triggered at network level, okay, by the corresponding control protocols, so RSVPTE, etc. To ensure the right network survivability, even if you lose communication, for example, with the controller. And the last point I wanted to mention for PCE is that there is no PCE function in the microwave controller, okay? And for the alarm event management, I think that what is important is to have also standard netconfig data models here, and be able to perform closed loop actions against the network. And for example, a specific alarm could trigger a new LSP optimization by the PC, for example. And last but not least, the telemetry collection. So we can also define standard interfaces based on netconfig or streaming telemetry, gRPC, for example, for feeding the event manager that then can trigger some network optimization based on threshold crossing alerts, for example, defined by the operator. And this telemetry data can be made also available through this standard interface, northbound interface, to the controller, to the hierarchical controller, but also to the external systems. For example, for if they require some detailed information, like for service assurance or big data analysis. I will conclude with some key functions of the hierarchical controller. So the end-to-end transport network control that the hierarchical is assuming since this entity will provide the cross-layer end-to-end resources visualization and also the stateful control of provision transport connectivity services, including the cross-layer resource relationship. For example, how you map a layer 3 VPN, an IP VPN service, transport connectivity service on the optical resources, an optical connection, an optical channel created at photonic layer, for example, or also at OTN layer. You have all this cross-layer information of the service at the hierarchical controller. The multi-layer PCE, so it's an active stateful PCE also, but now you can calculate a cross-layer optimal path across. So for the IP over optical, so multi-layer path based on the multi-layer topology that is available at the hierarchical controller node. And with the collaboration, of course, of the PCs of the underlying SDN controllers, and so that you can find the best optimal path. And last but not least is the function of the service binding to these transport resources that the hierarchical controller is assuming. And once it obtains the best path is to implement the service with the right, with the specific SLA that was specified for this transport connectivity service. So let me now introduce Oscar that will introduce you to the Agile network part of the presentation.
Thank you very much. I am Oscar Gonzalez. I am leading the SDN initiatives in Telefónica. So I'll explain you a little bit about our motivations for the going towards an Agile network. So please, next slide. So today, the day-to-day life of a service provider for transport networks involves a wide variety of processes, and they require a lot of interaction with the network. One example of these processes is the network planning and network creation phase, in which you need a real-time and accurate view of what is happening in the network with different abstractions views. Today is that the set of operation support systems that handle this discovery, this activation, this provisioning, or for example, the fault management processes, they do require a lot of manual inputs and in many cases, a lot of integrations with each of the technology of every vendor. So these systems, they attach to the network in different ways. In some cases, they need to connect to the device directly via a command line interface, or for example, PSNMP for alarms. In other cases, they go through the network management systems. And in the case of the network management systems, depending on the development that was made for some integration, some functionality might be allowed or not. So there is not an homogeneous way to connect. So, for example, today we have Corban, TOSI, XML, FTP, and even with the new cases, we have some data models that are really completely vendor proprietary. So we need to shift this paradigm to a new paradigm where the transport network is programmable. It offers a northbound interface towards the operation support systems. It offers a vendor-agnostic view. This is technology dependent and with different level of abstractions. So the interaction and the day-to-day life of an operator is simplified a lot. So we'll see how we'll handle this. So please go to the next slide. So we are doing this by consolidating the interfaces towards the system and making our network, our transport network, programmable. So we are joining together in an initiative to have a concrete and specific specification on how the information must be exchanged between the control layer and the operation support system layer and within the control layers. So we are doing this basically by means of data models. So what we are doing is standardizing the data models across the different layers. So in that sense, we have a classification, a taxonomy of this set of interfaces, and we can differentiate between service models, network service models, which they are a representation of a set of configurations that create a transport connectivity service from the point of view of the network. And they include the technical details to be able to create this service. So they include all the relevant parameters that you need to set up a given service. Take into account that this is from the perspective of the network, so it does not include the low-level details of the device. Also, we have network topology models that represent the relationships between the different network elements, for example, between the routers, between the ROADMs, between microwave devices, as they are discovered by the controller. So they represent the different layers in a vendor-agnostic fashion. So we are representing a DWDM network the same way, doesn't care which vendor it is. Then we have some path computation models, which they are really interesting because they allow us to use the functionalities of the path computation element that is part of the architecture as presented by Jeff before, and we can request computations to the network. So we can know whether it is feasible to deploy a LSP, or how could we go from one optical node to other with some kind of constraints. So they are really useful for the planning purposes. And finally, we have the devices model, which we'll talk about a little bit more later, that translate the requirements to the device-specific language, okay? So they are really the low-level details that you program within the device, and they cover all the very single parameters of the device. So really, they are a representation of a device in software. So we can manage it with a program like if it were a function. Okay. So next slide. So then, once we've seen this goal of consolidating the interfaces, we'll dig a little bit more in what we need for the devices. So we've mentioned before that we need to consolidate the interfaces towards the operation support system that can program the network, and then the controller can talk to the devices. And for that, we need, first of all, two main things. One common transport protocol that is able to communicate to all the devices regardless the vendor, and second, a unified data model. Sometimes it has happened as in the past that we have a correct transport protocol, but then the data model is completely different. So, for example, it was completely different programming a Cisco than a Juniper, than a Nokia, or an Infinera device. Okay, so here it is key, this data model that represents for example, a network instance, a configuration of a protocol, for example, the BGP protocol or the OSPF protocol. So this brings us to the second point, which is we are unifying this model for each technological domain. So our plan is that for all asset operators, when we buy a router of the IP/MPLS layer, that it has a well-known interface and data model. Okay, so we introduce a new device. We know how to handle it. So one for the IP/MPLS, another one for the optical devices, and another one for the microwave devices. So it's the same model per domain. And how are we going to choose which is the correct one? Because the choices are not few. I mean, in the industry forums and in the standardization fora, we have a lot of options. Okay, so we are not reinventing the wheel. We'll use standards that will be shown later, and we will select them mainly based on the maturity. Okay, so we know it takes a lot of time to implement natively in the devices a common data model. So we don't want to completely reinvent the wheel and say, okay, go start from scratch. So we'll take based on which are the more mature ones. And finally, we need to differentiate between two main parts of these interfaces in the devices. One of them related to the configuration of the device. So, okay, so there our main intention is that we are able to configure everything needed for running our network and running our services, and the telemetry that all the devices must have capabilities to provide real-time information of what is happening without impacting the performance of the device, which was one of the pain points in the past, that if we wanted to activate a lot of these remote measurements, for example, through SNMP, the CPUs was loaded and the performance of the device was harmed. So here we want to have a interface that provides real-time telemetry that does not harm the performance of the device, and that provides the information in a unified data model. So with all these elements, we can really build a agile and programmable network. So with this, I finish my presentation. So I give the word to Joy.
Thank you, Oscar, for the introduction. So my name is Lloyd Mphahlele. I'm a general manager for Transport in MTN Group. So I lead the transport evolution strategy across our markets in Africa and the Middle East. Okay, so just a little bit on, the use cases methodology. As you all know, use cases are a key element of this particular program. So it only makes sense that we follow some kind of methodology to ensure that, we achieve the ultimate outcomes for the working group. So if we can just, go to the next slide, please. All right, so here we touch on, the purpose of the use case methodology. So the idea really is to ensure that we don't take a big bang approach, and that we follow a use case by use case, basis approach. So if you look at one of, the things that we are, looking at, is to ensure that, the use cases, that are selected are chopped down into blocks, that are flexible and reusable, in the name of avoiding this big bang approach, that I spoke about. So these use cases are selected, from, the operators that are part of, the working group. So it comes from, the multiple operators. So the use cases are also, based on the operating environment, meaning we're taking an almost, design, thinking approach to the use cases, meaning that, the use cases emanate from the challenges that, the various operators have, in their their networks. And then, the next, objective is to, define, the subset of use cases based on existing standard. I think it is important to mention that, it's existing standard, and hence we've listed a few of the standard bodies here, like Open Networking Foundation, IETF, and Open Config, just to send, the message through that we are not, reinventing the wheel with what we are doing, in the MUST, working group. However, it is also important, to note that, if any gaps are picked up while we're working on this, use cases, some of, the modifications will be done to enhance, these use cases through collaboration with the standard bodies. The approach really promotes easy evolution. And I mean, just to give a sense, before this, with vendors, we will have, these automated tasks. But when we needed to do small modifications, the whole automation, script will have to be reviewed, which created complicated operational issues for most of the operators. So what we are seeking to do here is to make sure that this is done in bite sizes where we are able to operate in an agile manner. And then, of course, the aim is to select, the partners that we can go into, production with, and and do various RFXs with them. So the idea is that we co-innovate with the partners and also work together to select the vendors as indicated at the bottom there with vendor A, B, and C's, and of course using standard interfaces. If we can just move to the next slide, please. So we're taking a use case orientated strategy. As I said, use cases sit at the center of what we do. So in this particular slide, we outline the journey and the milestones within this particular journey. Right at the beginning, we're looking at the design. So this is the initial stage of the strategy. And in the design, I think what we're saying here is that I will improve in small steps value-based design of the next use case with the operations team, once again putting across the fact that it's a collaborative effort where these use cases will be co-designed amongst the operators. And then we are talking here of producing of a specification document. I think as we speak, right now we are sitting at an advanced stage where we have designed the white paper, and we are ready to share this with the industry. And this will be a continual process where we will produce the specification document. And the idea, I mean, is to also go into implementation, test and deployment phase, and ultimately production. Just some steps around this is that one of the important stuff is that the agile SDN design of the use cases will be defined by the operations team. The open knowledge technical specification will be based on standard modeling of these particular use cases, and also that the implementation of the use case will be done on a use case by use case basis as part of the roadmap of those particular vendors. So the one point that I meant to just highlight earlier on is that from the group itself, we don't see ourselves as high-level working group. However, the objective is to provide technical specifications for the industry as a whole on interfaces like, the northbound interface and the southbound interface, and in between, produce periodic reports that, will help, guide, the industry on what we're doing on open transport. If we can move to the next slide, please. So in order for us, to achieve our goals, we thought, it was important, to put together a taxonomy of use cases. In other words, categorize the type of use cases that we intend to pursue as, the operators inside of, this project. And, the operators in this particular working group are collaborating on common use cases spanning multiple operations. So these use cases, as you can see in the slide, they are grouped into 8 categories. So we have here the service provisioning use case, the inventory support, we have the topology, traffic engineering, support to performance management, network creation, support to fault management, as well as support to operations. So from the operators that we have, within the working group, they are at liberty to look at, use cases that are more relevant to their respective environment. I think, as a working group, we are now looking at, or we've agreed in principle to look at the layer 3, VPN use case, VPN provisioning use case that, we intend, to go on to next. So in each case, detailed requirements will be analyzed, and a set of interfaces, will be designed as an outcome of that. So if we can move to the next slide, please. Thank you. So the use case lifecycle is a very, very key component of what we're doing in the working group related to the use cases. So the use case design and validation, I think it's important to mention that it's a live and continuous process. As shown here is, it starts up with, the definition, and modeling of, these use cases. Standardization is a key component, as I indicated earlier on in the previous presentation, is that we don't, come up with our own standards from the working group. However, we work with existing, international standard bodies, and where, there are gaps, we will, converge, and then, chart a way forward. And then, this technical validation, and then activation. Of course, as part of, the use case life cycle, we have 3 key stakeholders here, which are, the operators, the vendors, and external organizations, which play, a key role in this life cycle, that I've mentioned, related to, use case being defined, modeled, standardized, validated, in operations, and most importantly, extended, to the rest of, the operations, to improve, the availability times, but also to just validate that whatever, that we are creating, within, these use cases, it's something, that is usable. It's something that is practically deployable by, the operators across the globe. So this is the use case lifecycle, in a nutshell. And I think this is my last slide. So if we can just move to the next slide, please. I would like to introduce Rob, who will take us through the network intelligence part. Thank you.
Thank you, Lloyd. So hello, my name is Robert Anner, and I'm a network architect at Telia Company Group Function. And I'm focusing on the network strategies we have, especially around Transport SDN and network function virtualization, and also things related to network automation in general. And in this final part of the presentation, we will be discussing network intelligence, or basically about what kind of applications or practical applications we foresee that the controllers could bring us, in addition to the immediate disaggregation benefits that we already mentioned earlier in the presentation. This also serves as a quick high-level showcase towards the use cases that the MUST group will be specifying later. So today, at least we operators know, but hopefully everyone on the industry knows as well, that in the future networks need to become much more automated, even to a level of no human operations needed. And that's in order for telcos to cope with the market demand, but also with the cost pressure we have in general within the industry. The automation is of course obtained through more intelligent software pieces instead of doing manual actions. And deploying this controller architecture that was presented earlier will allow us plugging those software functions against the network. So with this concept, we aim to provide not only programmability capabilities, but also more awareness of the state of the network, and through that, the ability to take real-time actions based on the seen state of the network. The architecture that has been presented, it doesn't specify necessarily where these software functions are realized. Someone might implement them coupled with the controller software, but the main driver here is, of course, to be able to utilize the open APIs provided by the controller. So that is really the key aspect, where the controller provides access to the information provided by the network and provides through that an ability to act against the network through the APIs. We have listed here a few examples of the cases where we think these applications will be realized through the controller architecture. Of course, first one is the end-to-end automated service provisioning. It's quite self-explanatory basic capability. But on top of that, we foresee, for example, on-demand service provisioning, different type of in-operation or maintenance support applications, then functions related to network discovery and inventory information handling, but also visualization tools and traffic engineering. Of course, some of these things already exist today, but often they are handled manually or through proprietary software and interfacing solutions. So the driver is here especially to make those applicable in the standardized environment as well. In the next few slides, we can look more deeply into a few of the examples. So if we move on to the next slide, there we have an example of in-operation network planning and more optimized operations within provisioning especially. So today, telcos hold quite large amounts of data, but due to low software capabilities we have in the networks, we are often unable to leverage on that data effectively. This leads to a situation where, coupled with low visibility and low predictability on the traffic patterns and manually driven change management processes, we often have long planning cycles and long development cycles, and therefore the upgrading of the network needs to be done with long-term planning in mind. So in practice, in order to guarantee that the network can support the forecasted traffic and deal with different failure scenarios, often additional spare capacity is installed well in advance, which then of course increases the network's CapEx spend unnecessarily. By having more up-to-date information from the network, our network planners can more accurately predict traffic usage and optimize the network build-outs to better fit the actual need, and therefore we can in general reduce the money we spend on the network infrastructure. Similar type of software capabilities could be also applied for on-demand service provisioning, whereas today we might provision services well in advance, and those might stay in the network even after the customer has stopped using those. But by doing the provisioning exactly when the service is going to be used, it will also free up capacity and also enable better offerings towards our customers. Third example where this similar pattern could be leveraged is, for example, the maintenance or operations of the network. So unfortunately, too large portion of service interruptions today originate from configuration errors that humans have made, for example, during maintenance windows. But with the right type of software, certain actions could be automated, and therefore we could minimize the amount of human errors. So all of these are kind of the prerequisite is for us having access to the network data and being able to act against it during the network operation phase. The following slide continues with a few other examples. These are more related to better handling of the network information and also our capability to actually do traffic engineering within the network. Today, the inventory management in telcos is quite top-down driven. So we manage network data by manual interaction with an inventory system. The data in the inventory is often outdated. So of course, operators are looking into the way how to keep those databases more up to date. And those methods are usually not effective enough because the only way to get true inventory data, which is always accurate, is to, of course, gather it from the network itself. Integrating with proprietary APIs is quite a task. So what these open APIs and a single interface point like SDN controller against the network could provide is a place where this information can be discovered and gathered from the network, affiliated to an inventory. The same data could be also used to better visualize the network in real time or even retroactively. And this would aid different kind of troubleshooting activities or any other operations that we do within Operations Center. So people wouldn't need to rely on their knowledge on the CLI as the only tool. They could also see pictures, and that would, of course, help people happening in the network and how the traffic is flowing. The SDN controllers, of course, also provide a platform for different type of traffic engineering functions, which can be run on top of the network. So today, many optimization tasks we do and audit handling, especially, are performed manually, meaning that the engineers might start examining the traffic patterns after a cable has been cut or something has happened in the network. In the future, we could have different software components taking over, switching the traffic to another link, or even doing calculations before the fault even occurs, because often you can spot different faults. You can predict faults based on the status on the network even before the fault itself happens, and then move the traffic to another link preemptively. Hopefully, in the end, the goal of this is to move guys who are today working in the Resource Operations Center from actually firefighting different problems to focusing more on service optimization, quality control, and different development activities on the networks. Then on the following slide, and as a last point for this section, I would like to connect this to the bigger picture that's currently being drawn within the industry, and that's the role of transport networks in the 5G slicing. So going forward, and quite soon, actually, different operators are assumed to be able to set up and monitor end-to-end 5G slices, and this touches as well the transport domain as one of the subdomains for the end-to-end 5G slice. The expectation is that there will be an orchestrator which will request a transport connectivity with specified SLAs, and the transport network with the control tools within the network needs to be able to provide that, and more importantly, the evolution of the transport follow the evolution of other, for example, virtualized core or radio domains and their evolution. So if other domains are capable of doing this, the transport needs to be able to do the same. And this is, as said, expected from us quite soon. Today, I would argue that we are quite well positioned when it comes to activation and provisioning of a slice. We can maybe quite easily tear down a transport connectivity as well. Of course, some things might still be hanging in the network, but when you consider the during operations optimization and traffic moving around, there are lots of things that we need to improve. And as said, this is something that we are expected to do quite soon. So we really need to set up this control architecture, the sooner the better. The Transport SDN architecture we have now here presented today, and is also presented on the white paper, is from our point, therefore, a key enabler for the future 5G network slicing automation within the transport domain. Next, I believe Victor will continue with his final remarks.
Thank you, Rod. Yes. So as we've explained today, disaggregation is accelerating. We are transforming our networks in a, let's say, exponential manner, we believe. This is a journey that we've started together. This programmability is the next step that we are willing to challenge the industry to help us to change the way that we are deploying, operating, and maintaining our networks. And we think that together we can reimagine the telecom network. So this is something that is not going to happen just because as operators we want to move the industry, but we need the rest of the community that is around. This mandatory use case requirement for SDN and transport subgroup is going to happen if we have the support of all the different players that will impact the evolution of these technologies. I was willing just to conclude the session or to finish the session asking you to join us. If you think that you can contribute in any area that we are covering or that we haven't pointed out that you think that you can give us feedback for this initiative, we will appreciate it. And thank you very much. If you want to know something else about the telecom infra project and the activities that we are doing together in this community, please go to the website, and thanks a lot for your time.